NASA expects to launch the James Webb Space Telescope, the largest and most expensive instrument ever flown.
The greatest scientific missions of modern times.
When the James Webb Space Telescope turned its gaze toward the mysterious object known as Oumuamua, the astronomical community braced for a historic moment. This was no ordinary celestial body. Detected in October 2017 by astronomers using the Pan-STARRS 1 telescope in Hawaii, Oumuamua baffled scientists from the outset as the first known interstellar object to pass through our solar system. Its trajectory and velocity confirmed that it came from outside our cosmic neighborhood. For years, speculation about its origin and nature ran rampant. Some believe it to be a rogue comet or asteroid expelled from a distant star system, while others propose far more exotic theories suggesting artificial origins. Until now, all that speculation had been built upon indirect data, visual tracking, light curves, and infrared readings, without a definitive image of the object. That changed when the James Webb Space Telescope, with its unparalleled sensitivity and resolution, finally delivered humanity's first real image of Oumuamua. Positioned 1 million miles from Earth at the second Lagrange point, the telescope's infrared capabilities pierced the veil of distance and time, revealing details that had been impossible to see before. This was no blurry speck against a grainy backdrop. It was a high-resolution capture of something that defied easy classification. Contrary to earlier depictions of cigar-shaped rock tumbling end over end, Webb's image showed a complex, almost prismatic geometry with facete surfaces resembling the fractured planes of a crystal or even the angular hull of something engineered. The coloration deepened the mystery. Some areas reflected light like metallic or icy compounds, while others were dark and carbon-rich, absorbing most incoming radiation. Certain regions even displayed an iridescent shimmer, like oil on water. Spectral data embedded in the image revealed an unexpected chemical cocktail: solid hydrogen in unusual concentrations, exotic ices containing oxygen and nitrogen in configurations never before catalogued, and compounds suggesting the object formed in an environment far colder than most known planetary systems. These findings raised compelling questions. Was Oumuamua born near a rogue planet, a brown dwarf, or within the icy mantle of a protoplanetary disk around a failed star? The image also shed light on its motion. Instead of tumbling chaotically, Oumuamua rotates steadily along a principal axis, completing a revolution every 8.3 hours, implying cohesion greater than a loose pile of rock and ice. This hints at a monolithic structure or one reinforced by chemical bonds or even metallic strength. Its thermal properties added another twist. The object heats and cools far more slowly than expected, suggesting internal insulation, perhaps a porous matrix that traps heat or even a hollow core. While a porous body would struggle to survive interstellar travel, a hollow structure raises a tantalizing possibility of artificial origin, though that remains speculative. Regardless, this image has transformed our understanding of interstellar travel. Oumuamua is not just a passing visitor. It is a time capsule carrying the chemistry, physics, and history of its birth system. The Webb telescope's capture offers a glimpse into the diversity of planetary formation across the galaxy and confirms that planetesimals can be ejected from one star system, journey for millions or even billions of years, and eventually visit another. The discovery underscores that the Milky Way is not merely a collection of isolated solar systems, but a vast, interconnected network where material flows across unimaginable distances. The implications for planetary science are profound. Before Oumuamua, models of planet formation treated star systems as largely closed, self-contained environments. Now, the open exchange of material between systems must be considered. If one such object entered our solar system, it stands to reason that countless others have passed through unnoticed. The James Webb image proves we now have the capability not only to detect these visitors, but to study them in extraordinary detail. Future encounters can be anticipated, analyzed, and perhaps even intercepted. This also revives a tantalizing idea of panspermia, the theory that life, or at least its chemical building blocks, can be distributed across the cosmos by wandering celestial bodies. While Oumuamua may not carry life, the complex molecules detected on its surface suggest it could transport organic compounds. If an object like it had crashed into a young Earth, Mars, or Europa, it might have deposited materials that contributed to the origin of life. Thanks to Webb's data, scientists can now examine whether such molecules could survive interstellar travel and how they might be altered by cosmic rays, extreme temperature changes, or the vacuum of space. In a broader context, this image marks a turning point. We are no longer restricted to studying our solar system's objects or observing distant stars as little more than points of light. We can now directly investigate the shape, motion, and composition of interstellar matter. The James Webb Space Telescope has become more than a lens. It is a bridge connecting us to far-off worlds and the silent travelers between them. Equally important is what the image does not show. There are no outgassing vents or comet-like tails, no obvious propulsion systems, no detectable emissions, and no signs of biological activity. Yet its strange geometry and remarkable durability resist simple explanation. Oumuamua doesn't fit neatly into existing categories like asteroid, comet, or dwarf planet. It may represent an entirely new class of interstellar phenomena, forcing us to rethink long-standing taxonomies and our understanding of the architecture of space. The cultural and philosophical impact is just as compelling. For millennia, humans have looked to the stars and wondered if we are alone. In its silence and mystery, Oumuamua reminds us that the universe is brimming with surprises, many perhaps beyond our current comprehension. The Webb image is not merely a portrait of an object. It is a reflection of our place in the cosmos. It confirms that the universe is dynamic, alive with wanderers carrying the secrets of other stars. Astronomy, at its heart, is a dialogue between light and time, and the light from Oumuamua has traveled for millions of years, across emptiness, through countless encounters, before reaching our instruments. With mirrors polished to atomic precision, Webb has transformed that light into knowledge, offering a glimpse into the unknown and challenging us to question our assumptions. This moment marks a shift in both capability and ambition. For decades, telescopes have expanded our view, but Webb has sharpened it, changing not just what we see, but how we see. We are no longer passive observers. We are active participants in a galactic story, one that includes visitors like Oumuamua and countless others yet to be discovered. There is a quiet reverence in knowing that a fragment from another star system passed through ours, and that we had the tools to witness it in detail. The image doesn't answer every question. It raises more than it resolves, but that is the nature of discovery. In the end, it is not just a snapshot. It is a beginning of new science, new theories, and perhaps one day, new contact with a wider tapestry of the universe. Oumuamua has already slipped beyond the reach of most telescopes, fading into the deep black of space. But the image remains, a record of an encounter that whispers of the infinite and the unknown. As scientists continue to analyze the data, refine models, and debate its origins, the rest of us are left with something just as powerful, the wonder of it all. The James Webb Space Telescope has given us more than just a view of an interstellar visitor. It has given us a reason to look farther, think deeper, and dream bigger. For the first time in human history, a telescope has captured the unmistakable features of an object from another star system in such exquisite detail that an entirely new chapter in interstellar studies must be written from scratch. It is more than a photograph. It is a portal into alien processes, sculpted in deep time and cast across a galaxy. Researchers immediately began rethinking what interstellar objects could be. No longer limited to the blurry approximations of earthbound telescopes or the low-resolution tracking of older instruments, the clarity of Webb's image shattered long-held assumptions, not only about shape or material, but about how such objects could be ejected from their home systems, survive millennia adrift in space, and remain intact upon entering another solar system. This unprecedented visual record inspired scientists to model entirely new ejection scenarios, such as bodies formed under extreme tidal forces near the edges of accretion disks, flung into the void by chaotic gravitational interactions with massive superjovian exoplanets, or born as fragments of catastrophic planetary collisions. The fine resolution also allowed researchers to measure light reflectance from distinct surface zones, each bearing unique spectral signatures. Some regions appeared coated in highly reflective, possibly metallic compounds that responded oddly to infrared light, while others absorbed nearly all incident light, exhibiting a chemical profile similar to tholins, complex organic molecules forged through prolonged radiation exposure. These sharply defined zones were not blurred as if by erosion or impact. Instead, they were cleanly separated, suggesting a process of surface differentiation, a trait typically reserved for much larger planetary bodies, not an object only a few hundred meters in length. This raised the possibility that Oumuamua was a fragment of a more complex parent body, one massive and hot enough to separate its elements by density or composition. If true, this would mean the object was not simply a rogue rock, but a shard of an ancient, perhaps destroyed world, a geological time capsule from a planetary system that may have vanished eons ago. This perspective prompted exoplanetary scientists to scrutinize its irregular surfaces more closely, revealing signs of a long and storied journey, micrometeoroid pits, deep grooves, and a thin veneer of exotic ice. Yet one of the most curious findings was its surprisingly dust-free exterior. Over millions of years, drifting between stars, it should have accumulated interstellar dust, but Webb's image showed it to be unusually clean. This absence of dust hinted at a form of natural cleansing, perhaps through sublimation, spin-related shedding, or, more controversially, an active process from the object itself. Some physicists suggested a subsurface layer of volatile materials that, when heated by solar radiation, could generate localized bursts of gas to push away fine particles. Others speculated about electrostatic or electromagnetic effects created by mechanical stress during its voyage, potentially producing fields strong enough to repel dust. Such phenomena had never been seriously considered for small interstellar objects and could fundamentally change our understanding of microscale interstellar physics. The precise measurement of Oumuamua's rotation rate, made possible by Webb's image, only deepened the mystery. Unlike the chaotic tumbling seen in most irregular objects, its steady, balanced spin suggested unusual internal cohesion, or even deliberate stabilization, prompting some theorists to cautiously revisit controversial ideas of alien probes, light sails, or derelict technology. While mainstream astrophysicists lean toward natural explanations, the sharp angular symmetry of certain facets, the reflective materials, and the clean separation of surface zones made such possibilities harder to dismiss entirely. Adding to the intrigue, thermal mapping revealed uneven heat distribution across the object, even after accounting for rotation and solar exposure. Some areas retained warmth far longer than expected, implying either an insulating outer layer or, more astonishingly, a heat-retaining core. Although some comets display similar thermal behavior, none have exhibited it at this scale or origin. The possibility of a layered internal structure opened new discussions about how interstellar fragments cool, how internal gases migrate, and how radiation reshapes their chemistry over time. The implications reach beyond astronomy into astrobiology, as Oumuamua's differentiated layers, radiation-weathered surface, and complex chemistry suggested it could serve as a vessel for organic compounds. Unlike simple icy comets or chondritic asteroids, it seemed capable of shielding, preserving, or even catalyzing prebiotic reactions over vast interstellar timescales. In response, some laboratories began recreating Oumuamua-like conditions in vacuum chambers, bombarding synthetic materials with radiation while rotating them to simulate the object environment, hoping to unlock the secrets of how such a relic could survive and what it might carry across the galaxy. Researchers began slowly simulating Oumuamua-like conditions in cryogenic environments to test whether amino acids or nucleobase analogs could survive an interstellar journey, and, if so, whether they might arrive intact on habitable planets. The idea of lithopanspermia gained renewed traction, not as myth but as a plausible mechanism for seeding life across the cosmos. Webb's revelation of Oumuamua provided the clearest case yet that such a process might not only be possible, but perhaps even common. The image also sparked speculation about the nature of future interstellar visitors. If this object was so complex, what might the next one bring? Could it carry isotopes never before detected? Could it spin in seemingly impossible patterns or respond to solar radiation in ways that defy current physics? Webb's achievement prompted astronomers to re-examine archival data for overlooked candidates and inspired the design of new monitoring systems to detect such objects early enough, perhaps, to launch missions to intercept or rendezvous with them. Space agencies began drafting mission concepts for the next interstellar visitor. The ability to image Oumuamua so precisely stirred ambitions to go further. Proposals emerged for high-speed probes equipped with high-resolution cameras and mass spectrometers, powered by solar sails or compact nuclear reactors, capable of flying alongside a future analog and returning real-time data on its composition, structure, and possibly even its origin. Meanwhile, theorists proposed using Webb to conduct a deep survey of the region of space from which Oumuamua had come. If one object had been ejected from its system, Perhaps others followed, a drifting family of rogue bodies born from planetary collisions, failed stars, or ancient debris fields. Webb sensors could, in theory, detect subtle background infrared variations betraying the presence of such fragments. As the scientific implications multiplied, so did the philosophical ones. The realization that an object older than human civilization, perhaps older than life on Earth, had passed within a cosmic stone's throw brought a renewed sense of humility. Oumuamua was a shard of a distant place, a silent messenger from a past we might never fully know. It carried no signal, issued no greeting, and yet in its silence it spoke more than volumes of speculative fiction ever could. There was something haunting in its symmetry, something graceful in its path. Webb's image, frozen in time, showed not a ruin but a survivor, hardened by starfire and gravity, sculpted by cosmic weather, shaped by forces humanity has only begun to understand. It didn't need to be artificial to inspire awe. Nature, after all, is the oldest engineer. The moment reached beyond science into culture. Scholars in the humanities examined the event's meaning, while artists, poets, and philosophers explored how the image shifted humanity's relationship with the universe. This was not a telescope peering deeper into our own backyard. It was a keyhole view into someone else's. The colors, angles, and shadows became symbols in galleries and metaphors in literature. Webb's image bridged science and storytelling, offering a new lens through which to ponder origins, destiny, and the cosmic unknown. Educators seized the opportunity, bringing images of Oumuamua into classrooms and public lectures as tangible anchors for discussions on interstellar distances, orbital mechanics, and the nature of discovery. For once, teachers didn't have to rely solely on simulations or artists' impressions. They had a real image, a beacon from beyond. It's worth noting that all of this arose from a rare convergence of timing and fortune. Oumuamua entered our solar system just as humanity was developing the tools to detect such fleeting visitors, and Webb, perfectly positioned and tuned to the right wavelengths, was ready to capture it before it vanished into the abyss. That alignment of technology, curiosity, and cosmic happenstance will be remembered as a milestone in our quest to understand the universe. Though the object has now faded beyond the reach of direct observation, its legacy has grown. The image stands as both a benchmark of what is possible and a template for what's to come. It redefines the boundaries of observation and forces us to recalibrate our assumptions about the galaxy. In time, this single encounter may give birth to an entirely new branch of astronomy, the systematic study of interstellar visitors. With rapid advances in telescope technology, space-based sensors, and high-speed propulsion, it is likely that Oumuamua will not remain the only interstellar object analyzed in such depth, but it will always be the first to reveal its true form, the first to be seen in full color, the first to whisper across light years and be heard. Even now, data from Webb's image continues to yield new insights, as more sophisticated algorithms tease out faint spectral signatures, refine measurements of its motion, and reconstruct its long and extraordinary history. Scientists are finding new ways to simulate how interstellar radiation affected Oumuamua's outer layers, how micrometeorite impacts shaped its form, and how gravitational forces from distant stars might have nudged it onto its epic voyage. For years to come, this one image will likely serve as a foundational reference across disciplines. In planetary science, it will redefine ejector mechanics. In astrobiology, it will influence models of molecular migration. In astrophysics, it will challenge conceptions of non-Caparian motion and radiation dynamics. Even in the nascent field of interstellar archaeology, the study of non-terrestrial artifacts, it may one day be viewed as a first specimen. And yet, even amid the immense scientific impact, the image carries something subtler, a quiet astonishment, a recognition that the universe is more vast, more complex, and more interwoven than even the boldest theories suggest. Oumuamua's passage is over, its moment in our sky past, but through Webb's lens, it lives on not just as a photograph, but as a revelation. As scientists delve further into the data supplied by the James Webb Space Telescope's capture of Oumuamua, a cascade of new hypotheses emerged, each more intricate than the last. This was not merely a moment of confirmation, it was a provocation. The clarity of the image brought with it a level of complexity no model had prepared for. Tiny shadowed indentations, ridges running parallel across certain planes, and sudden geometric discontinuities told a story written in form rather than function. Even the orientation of its angular structure suggested interactions with unknown forces during its voyage, subtle influences that left permanent marks. Perhaps most unexpectedly, attention turned to how light interacted with the object in motion. As Oumuamua rotated, its surfaces didn't simply reflect infrared radiation, they refracted it in peculiar anisotropic patterns. This behavior was entirely alien to known natural bodies of its size, hinting at crystalline structures embedded within or perhaps coating the surface, with orientations aligned in ways suggestive of growth under extreme pressure, or perhaps artificial ordering. Laboratory attempt to recreate similar reflection patterns fell short, unable to mimic the sharp transitions and bandwidth of reflected wavelengths seen in Webb's data. This further opened the field to consider materials we have yet to encounter in nature, or those formed in environments beyond Earth's understanding. Regions near neutron stars, around magnetic white dwarfs, or in the interstellar medium under intense galactic cosmic rays. Even more compelling was the asymmetry in the object's thermal signature. As Webb's instruments tracked its retreating path, it became clear that heat dissipation on one end of the structure occurred at a significantly slower rate than on the other. This discrepancy could not be explained by simple surface variation or orientation alone. One prevailing theory proposed that the end of the object with slower heat loss possessed a layered substrate of exotic ices trapped beneath a dense mineral crust. This structure might have formed through slow accretion in a distant solar system where volatile compounds like ammonia or nitrogen became encapsulated under silicate-rich layers. While such intricate mineral stratification isn't unprecedented in large celestial bodies, for an interstellar object of this scale, it challenges all prior assumptions. It suggested that planetesimals could undergo complex differentiation before ejection, a process thought to be reserved for much larger bodies. This opened new lines of research into intermediate-scale celestial chemistry, raising the possibility that small objects might hold surprisingly diverse mineralogies depending on their stellar origin. Mineralogists, geophysicists, and astrochemists quickly mobilized to create reference datasets that might one day match what Webb had observed. A separate line of inquiry focused on the object's resistance to solar radiation pressure. When Oumuamua first left the inner solar system, its acceleration pattern defied classical expectations. Webb's image allowed researchers to recalculate its mass-to-surface area ratio more precisely, revealing it to be remarkably low for an object of such shape, implying a thin, lightweight structure rather than a dense solid core. This finding, reinforced by the image's dimensional resolution, reintroduced earlier theories that Oumuamua might be a foil-thin construct, possibly a natural sheet-like formation, or, more provocatively, something engineered. Such low-density forms do occur in space, but usually as fragments of cometary tails or ejecta clouds, not as intact bodies with angular integrity. Material scientists became particularly intrigued. If Oumuamua was indeed extremely thin yet structurally cohesive, it could serve as a model for interstellar sail dynamics. In this context, the object's apparent responsiveness to solar radiation wasn't an anomaly, it was a feature. The interaction of light and force might have subtly guided its journey through the solar system, offering insights into passive propulsion mechanisms that future spacecraft could harness. This possibility reinvigorated research into solar sail design and passive navigation, with the idea that nature might have already perfected what human engineers are only beginning to explore. Looking beyond structural analysis, the Webb image also opened up an entirely new realm, surface topography as a chronicle of time. The object's skin, as revealed in Minute Contu, seemed like a stratified document, recording impacts, radiative degradation, and perhaps erosion from gas-rich environments. Advanced photometric modeling revealed subtle depressions on one face consistent with sustained exposure to particle winds, suggesting a past passage near a highly active stellar corona. If true, this meant that Oumuamua's voyage brought it not just through cold vacuum, but through regions of high energy that left visible scars on its body. These regions could be mapped, cross-referenced with simulations of stellar neighborhoods, and potentially used to trace the object's point of origin with greater accuracy. By treating the object like a planetary surface in miniature, planetary scientists used slope measurements and reflectivity gradations to estimate regolith properties. The findings suggested that Oumuamua might have carried a fine layer of granulated material, dust grains electrostatically bound to its surface. Unlike lunar dust, this hypothetical regolith had a spectral profile skewed toward carbon-rich compounds, perhaps shaped by billions of years of exposure to galactic cosmic rays. This hinted at a particle history unlike anything within our solar system, a tangible representation of how matter evolves when unbound from gravitational wells. Perhaps most curiously, embedded within one of the image's spectral layers was a sharp, isolated spike in absorption, detected only once and only within a narrow band of the near-infrared spectrum. This anomaly couldn't be matched to known absorption lines from common molecules or minerals. Spectroscopists puzzled over it, theorizing it could correspond to an unknown complex organic compound or perhaps a lattice vibration mode in an exotic crystal structure. Efforts to recreate the spectral profile in simulated lab environments are ongoing, but so far, the anomaly resists categorization. If it holds up under further scrutiny, it might represent the first observational evidence of a previously unrecorded material class. Meanwhile, attention also turned to the broader environmental implications of such interstellar crossings. If Oumuamua could survive a multi-star journey, what sort of damage might it suffer, or inflict, if it collided with a planetary body? Studies began modeling the object's kinetic energy relative to planetary atmospheres, hypothesizing that interstellar impacts might differ fundamentally from intrastellar ones, not just in energy but in chemistry. The introduction of alien isotopes, high-energy crystalline fragments, or pressurized volatiles might have cascading effects on the planetary biosphere, depending on where and when they landed. This offered a new dimension to planetary defense research, preparing for not just asteroids, but cosmic interlopers with unknown properties. At the same time, theorists turned to the broader question of frequency. If Webb could image Oumuamua in such detail, and if this object represents just one interstellar visit out of many, then what else might be floating undetected in the gaps between planetary orbits? The idea emerged of an interstellar traffic model, a probabilistic framework estimating how often and under what circumstances such objects pass through solar systems. Using data from Oumuamua as a seed variable, astrophysicists began constructing simulations of galactic currents, stellar ejections, and gravitational pinball scenarios that might shepherd objects from one system to another. These models quickly revealed something startling. The rate of interstellar visitors might be far higher than assumed. We may simply lack the sensitivity to detect the majority of them, especially the darker, less reflective bodies or those moving at non-standard vectors. With this in mind, astronomers began advocating for the construction of next-generation sky monitoring arrays, not just to catch incoming asteroids, but to flag high-velocity outliers that defy Keplerian dynamics. Such arrays would work in concert with telescopes like Webb to ensure that when the next Oumuamua-like object arrives, humanity is ready. Do you want me to also tighten this paragraph so it reads smoother for a narration script rather than a research-style article? That would make it sound more like a documentary segment.